In this section, we want to solve systems of linear equations in three variables. So the system consists of three equations, each of which has three variables. So my first system is this, and notice that I've numbered the equations 1, 2, and 3. I want to start by adding the equations together two at a time, so I eliminate the same variable from two different pair of equations. Notice that if I add equation 1 and equation 2, my variable z will be eliminated. So I'm going to say 1 plus 2, and then I'll show you what I get. 2x plus 3x is 5x. 1y plus 4y is 5y. Negative z plus positive z is 0, and 3 plus 6 is 9. Now I've eliminated z from this pair of equations. Let's eliminate z from the first and third equations. That's a different pair of equations, and I'll do that by adding those. 1 plus 3 gives me 2x plus 2x is 4x. 1y plus negative 3y is negative 2y. And 3 plus 1 is 4. Now you see what I have is a system of two equations and two variables. Now I can solve this system for x and y in the same manner that I solved the systems in the previous section. So let's decide that we want to eliminate, it doesn't really make any difference, let's eliminate y from this pair of equations. So I'll multiply this first equation here by 2, and I'll have 10x plus 10y is equal to 18. Then I'll multiply the second equation by 5, and I'll have 20x minus 10y is equal to 5 times 4 is 20. Now when I add them together, 10x plus 20x is 30x, plus 0y is equal to 38. So I end up with x is equal to 38 divided by 30, which is 19 over 15. If I reduce this fraction to the lowest terms, I have 19 over 15. So this is the x-coordinate of the ordered triple that satisfies all three of the equations. Now, I need to find the y-coordinate and also the z-coordinate. So I can substitute x equal 19/15 back into any one of these equations and solve for the corresponding value of y. So let's take 19/15, put it back into this equation, and that will give us 5 times 19/15 plus 5y is equal to 9. Now 5 divides into 15 three times, so I have 19 thirds plus 5y is equal to 9. 5y is equal to 9 minus 19 thirds. Now 9 is 27 thirds minus 19 thirds. So let's see, 27 minus 19 is 8. So 27 minus 19 is 8 thirds. So 5y is equal to 8 thirds. I multiply both sides by 1/5, and I get y is equal to 8/15. Y is equal to 8/15. X is equal to 19/15. Now, if I substitute 19/15 and 8/15 back into any one of these equations here, I can solve for z. Now, it turns out when I do that, and I won't show the work, z is equal to 1/15. So you'll find z equal 1/15 when you back substitute here. So I get an ordered triple for my solution to this system. 19/15 for x, 8/15 for y, and 1/15 for z. That's an ordered triple of numbers. This is the only ordered triple that satisfies all three of these equations. Let's take a look at our next example. Notice in this system of equations right here, z has been eliminated from this equation. There's no x in this one, and there's no y in this one. I think it's easiest to solve the system if we rewrite it this way. X plus 3y, then we'll leave room for where z goes, is equal to 5. 6y plus z, so 6y plus z is equal to 12. And then x minus 2z is negative 10. So x minus 2z is equal to negative 10. Now it looks a little more confusing at first when some of these variables are missing, but actually it's a little easier because you only have to eliminate a variable from one pair of equations. So let's see, if we take this equation right here and add it to, how about if we multiply this equation by negative 1? So what will we get? I'll eliminate x from this pair of equations right here. So let me take this equation, x plus 3y is equal to is equal to 5, and then I'll take this equation and multiply through by negative 1. So I have negative x plus 0y plus 2z is equal to positive 10. So I multiplied this by negative 1, this by negative 1, and this by negative 1. Now if I add these two together, I get 3y plus 2z is equal to 15. So here's an equation that came from the system that involves only the variables y and z. I'm going to put that together with this equation right here that also only involves the variables y and z. So 6y plus z is equal to 12. So I only had to take one pair of equations here and eliminate one of the variables. I eliminated x, so I was left with an equation with y and z. I'll put that together with the other equation that involves only y and z, and now I'm left with a system of two equations and two variables to solve. This one I think I can do easily by taking my first equation, 3y plus 2z equal 15, and adding it to negative 2 times my second equation. So I'll multiply this by negative 2. I get negative 12y minus 2z is equal to negative 24. Now when I add these together, 3y and negative 12y, negative 9y, plus 0 is equal to negative 9. So y is equal to 1. Y is equal to 1. I'll take that and substitute it back into an equation that just has y and another variable. How about if I substitute this back into this equation? Then I get x plus 3y equals 5. So x plus 3 is equal to 5. That means x is equal to 2. So I'll take either x equal 2 or y equal 1 and substitute it back into another equation. Let's see, how about if I go back to this equation right here? So x, which is 2, minus 2z is equal to negative 10. So I substitute x equal 2 into this third equation. 2 minus 2z is equal to 10, minus 2z is equal to negative 12 when I add negative 2 to both sides, so z is equal to 6. So I'll put these three solutions together, and that'll be the solution to my system. X equal 2, y equal 1, and z equals 6. And that's the only ordered triple that satisfies all three of these equations.